Hello everyone, and welcome to a new lecture on mechanics. In this lecture we will start a new and last chapter on fluid statics. And we will actually start with discussing three important principles when dealing with fluid statics. Fluid statics is also known as hydrostatics, where a fluid is a liquid or a gas. And the difference between liquids and gases and solids is that the former cannot support shear forces when at rest. In other words, they take the shape of the container in which they're put. In this course, we will deal mostly with incompressible liquids. Now, everything else is similar to what we've studied so far, so we will use the same equilibrium principles that we learned. And in addition, we will have to be able to determine the type of loading that is imposed on structures by fluids. And therefore, for this purpose, we will study the three important principles. So once we understand these principles, we should have no problems determining the loads acting on a structure, and then we can simply apply the equations of equilibrium and solve for the unknowns. So let's start with the first principle, which states that the pressure at any given point in a fluid is the same in all directions. This is a principle which is also known as Pascal's law, as it was discovered, established by Blaise Pascal, a French physicist. So what this principle means is that, for example, if we are in a fluid, within a fluid, and we bring a special gauge, a pressure gauge, a gauge that can measure the pressure in the fluid in a given direction. If we place the pressure gauge horizontally and we measure the pressure, the horizontal pressure, and record the value, and then in a second instance, we do the same thing, so we have the same pressure gauge, but now we rotate it, for example, by 90 degrees clockwise. So we're now measuring the vertical pressure upwards, vertical pressure in the upwards direction. Or in a third instance, for example, we rotate the pressure gauge from the original direction counterclockwise by 90 degrees, and now we measure the pressure, the vertical pressure in the downwards direction. Or we can rotate that pressure gauge in any other direction at that point, which is in all cases located at the same depth h from the surface of the fluid. And in all of these cases, the reading of the pressure gauge will be identical. So in other words, as the first principle states, the pressure will not change at a given point in a fluid depending on the direction in which it is measured. So it's equal in all directions. The pressure at a point is equal in all directions. The first principle. Now, the second important principle that we need to understand is related to the direction of the pressure. And it states that the pressure always acts perpendicular to any surface. In other words, the pressure intensity vectors are always perpendicular to the surface on which they act. So Again, for example, if we have, say, an inclined surface and there is a fluid acting on the left-hand side of this surface, something like this. These are the pressure intensities, and they are all perpendicular to the surface. So they always make an angle of 90 degrees to the surface. No exception about that. Now, if we were to draw a case like this one, in which the pressure intensities are at another angle than 90 degrees, then this is incorrect. We should never draw the pressure intensities at an angle that is not perpendicular to the surface. Pressure always acts perpendicular to any surface, and that's the second principle. Finally, the third principle helps us determine the magnitude of the pressure, and it states that the pressure increases linearly with the depth. And we can relatively easily show a proof of the third principle by considering a very small, infinitesimally small element of the fluid having a cross-sectional area dA and being located at the depth h from the surface of the fluid and having a small height, very small height dH. So this element is within the fluid, so it's acted upon by pressure all around. The pressure acting on the top surface will be equal to P times dA, and the pressure acting on the bottom surface will be equal to P plus an increase of pressure dP times dA. And of course, the third force acting on this element, it's its own weight. The weight equals to the density of the fluid times the acceleration of gravity times the volume, so equals to rho g dA dH. If we sum the forces on the vertical direction for equilibrium, we get P plus dP times dA minus P dA minus the weight rho g dA dH equals 0. And we can cancel out P dA in this equation. And that gives us rho g dA dH equals to dP dA. And again, we can cancel out dA here. And therefore, dP from this equation equals to rho g dH. So in other words, we can state that a change in pressure occurs with a change in depth. Very simple. A change in pressure occurs with a change in depth. Now, what we can do next, we can integrate both terms on the left side and right side of the equation. And by doing so, we can establish an important relationship, which is P equals to rho GH. So P varies linearly with H because rho and G are constant. Now, in general, we can write this expression as P equals to P naught plus rho GH, in which P naught is the pressure acting on the surface of the fluid, where we start measuring the depth from, so where H equals to 0. Now, this is a very important relationship, and it tells us again that the pressure increases linearly with the depth. So that's the third principle. So whenever we draw pressure diagrams, they will always vary linearly with the depth. So they will not be constant and not parabolic. They will vary linearly with the depth. So now we have established the three principles. If we can master these principles, then we can start solving questions. And thank you very much for attending this lecture. In the next lecture, we will attempt solving a typical hydrostatic questions by applying this these principles.